Okay, welcome back. Now, we've been talking a lot about the mass and spring system, so in this video we're going to talk about other physical systems that demonstrate simple harmonic motion. So we're just going to be looking at a bunch of examples. In each example we're going to take a look at a physical system, we're going to see what forces are involved in that system, and we're going to see if we can recover the characteristic differential equation for simple harmonic motion. Second derivative of displacement with respect to time is equal to negative omega squared times the displacement. So let's first start off with a nice and basic example. Let's talk about a vertical mass and spring system. You thought we were done with mass and spring. Now this actually shouldn't be too bad. Just really want to point this out first because in all the other cases we've been dealing with a horizontal mass and spring system. And I want to show that even when you have it like a mass and spring in a vertical position, it still works. So let's start off by saying that we just have our free spring just hanging right here. Nothing attached, it's at its natural length. Now, unlike before in the horizontal case, once when we attach the mass, we have gravity acting. So when we attach the mass, it's going to be pulled down slightly. Now, let's just say that aside from that, it's not moving. It's just in this new equilibrium. And in this new equilibrium, all the forces are balanced out. And what I mean by that is that the force from gravity pulling the mass down is balanced out by the fact that the spring is stretched slightly and is pulling back a little bit. So we're going to say the Hooke's force here. And let's just say that it's moved down a distance, let's call it delta L. That means we can describe what's happening at this equilibrium. We can say that the force of gravity is balancing with the Hooke's force, which is the same as saying that the mass times gravity is equal to our Hooke's force, which is K times delta L. Okay, so that's all well and good. But now let's see what happens if we displace it from this new equilibrium position. So let's say it's resting really nicely, but then we tug it down. Let's call it a distance x. And let's just define x to be positive in the down direction. So what's going to happen? Well, unlike before in this case here, the forces aren't balanced out here. We've stretched the spring out so that there's going to be a greater Hooke's force or a greater spring force trying to restore it to equilibrium. So let's just write out our equation of motion. So let's take a look at the net force. That's going to be equal to our gravity going down or in the direction of our positive x minus the Hooke force pulling up. So we know the Hooke's force is K times the displacement, but this time we're going to look at the total displacement, which is going to be delta L plus x. That's the total amount this spring has stretched. And that's going to be equal to ma. So let's just distribute this K out. So we're going to get mg minus K delta L minus Kx is equal to and since our acceleration is in the x direction, we can rewrite it as second derivative of x with respect to time. Now this, at first, this doesn't exactly seem like simple harmonic motion, considering we have these extra terms right here. But we can relate them with our equilibrium condition. We found that at equilibrium, or just in general for the system, that the mass times gravity is equal to this K delta L, which means we can plug that in here. Let's say plug this right in for mass times gravity, and we'll find that these two terms will cancel because they're equal, which means that we're just left with this right here. So let's just rearrange this a bit, divide by m on both sides, so we're going to get second derivative of x with respect to time is equal to negative k divided by m times x. And this is the same exact equation we had as before with our horizontal mass and spring. So this is simple harmonic motion provided we have omega squared defined as k divided by m, which means that this mass will bob up and down with a period defined by 2 pi times radical m over k. So there we have it. The horizontal, we get the same result with the vertical spring system as we did with a horizontal spring system, provided that we measure the displacement x with respect to the position of the new equilibrium. So that's pretty simple. Let's just do one other quick example. Let's do a rotational case. In all the systems, we've been working with linear motion. So let's take a look at this system here. Here we're just going to have a wire dangling down from and at the bottom of this wire here, we're going to have a nice cylindrical mass. Now, we're not actually going to give this linear motion. We're not like going to push it or pull it. We're going to give it rotational displacement by twisting it. So we can describe our rotational displacement by theta, the angle displaced. And lucky for us, there is a rotational form of Hooke's law. But instead of dealing with forces, we're going to be dealing with the rotational analog, torque. And the torque in this case is going to be in the opposite direction of displacement. It's going to be proportional to the displacement theta with a constant of proportionality kappa, which is like the rotational analog for our spring constant, K. And actually I shouldn't say that because this kappa is what we call the torsion constant. Torsion constant. And this, like the value of this torsion constant is based off the physical properties of the wire. So properties like how thick it is, or the radius of the wire, or how easily it can twist, etc. So now that we have a expression for like the torque in this system, let's apply that to our rotational equation of motion, which is the net torque has to be equal to, instead of mass, we're going to be dealing with moment of inertia, the rotational form of mass. Instead of acceleration, we're going to be dealing with angular acceleration. And since this is the only torque, we can just plug we can just plug that in right here. So we're going to get that negative kappa times theta is equal to moment of acceleration I times our angular acceleration. I'm just going to rewrite that as second derivative of theta with respect to time. And you can easily see once when we divide by I on both sides that we rediscover our characteristic simple harmonic equation. We're going to get second derivative of theta squared with respect to time is equal to negative kappa divided by I times theta. So this is the equation for simple harmonic motion with omega squared defined as kappa divided by I, which means that this mass and the wire, it'll twist or rotate back and forth with simple harmonic motion with a period given by 2 pi times radical I over kappa. Looks like I'm running out of time, so we're going to talk about more examples in the next video.